So again, we have here V equals V root mean square, root 2 sine of 2 pi ft. Then we have just the capacitor. So we begin with the same idea. Voltage of the capacitor is equal to Q over C, right? Which is equal to the voltage of the source, which is V root mean square root 2 sine of 2 pi ft. And then the Q is just equal to V root mean square C times root 2 times sine of 2 pi ft. Now to get the current in the circuit, I take the derivative of the Q. See, a minute ago, we integrated it. So I take the derivative dq dt, and the derivative of sine is cosine, and then 2 pi f comes out. So we've got this thing now in front, and we can rewrite this so that it's like this. 2 pi f c times v root mean square times root 2 times, and then can we rewrite this as a sine? Cosine is a sine 2 pi ft, and then what should I put here for the phase angle? The other one we put a minus, right? This one is a plus. You put a 0 here, sine of pi over 2 is 1, so cosine of 0 is 1 also. So whatever this thing is, we go through that same argument again. It must be the current that the ammeter will measure. So this is I root mean square. Or I can rewrite it like this. I can rewrite it as V root mean square divided by quantity 1 divided by 2 pi Fc. Okay, now why do I go through the trouble of rewriting this simple looking thing into this weird looking thing? Okay? Why do you think I go through the trouble of doing that? Because I'm about to define something new, right? What am I about to define? Look back at what we did with the other one. Remember symmetry always. Symmetry, symmetry, symmetry. So whatever this is must have units of ohms. And it must be how the resistor, how the capacitor resists the flow of electrons, right? So we're going to call it XC. Ohms, it has units of ohms. And it's called capacitive reactance. So here is a kind of weird, the capacitor is exactly opposite to the inductor. The inductive reactance was 2 pi FL. So in order for the inductor to resist the flow of electrons, you got to have the frequency high, inductor high. For capacitor, if you have the frequency high and the capacitance high, it actually likes that. The XC is low. So let's go back here and try to understand that again. So this thing drive the current back, forward, back, forward, back. Okay? So if you try to do that really quickly, the capacitor doesn't resist you too much. That's weird, huh? It's opposite to the inductor. Why? Go back, forth, back, forth, back, forth really quickly. Why doesn't it resist you? Who can answer? Remember the DC circuit. How does the capacitor resist the circuit? When you charge it up, it eventually gets to a point where its voltage is equal to the voltage of the battery, right? And it resists the battery eventually. So for the capacitor to resist the battery, you got to build up charge on it in order for it to act like an opposite battery. But if the frequency is high, okay, if the frequency is high, the current's going that way, current's going back, forward, back, you're not giving the capacitor enough time, enough chance to build up charge in any one direction. Before it's charged, you're switching the charge on it. Before it's charged, you're switching charge always. You're just not giving it enough chance to ever oppose you. So if the frequency is high and its capacitance is high, so it's completely opposite. If its frequency is high, capacitance is high, it doesn't have enough chance to resist you. Therefore, the capacitive reactance is low. But if the frequency is low, now it doesn't like it because it resists you more. So makes perfect sense, huh? Okay, so now let's go into the phase angle thing. The current is ahead of the voltage of the capacitor, right? Or we could write it this way. We could write the current as 0. We could write the current as I root mean square root 2 sine of 2 pi ft. And then we would write the voltage of the capacitor as what? Well, let's see. If the current is a plus pi over 2, it's ahead of the voltage of the capacitor. Therefore, if the current is a phase angle is 0, the voltage of the capacitor is behind the current in the circuit by pi over 2. So you could either say it either way. Now, to visualize this, now I'm going to introduce what's known as phasors. This is a great way to visualize what happens. The voltage of the source, okay, is always the same as the voltage in the resistor, because the only difference between them is IR, right, the current. And the current, therefore, is always in sync, in phase with the voltage of the source. Okay? Now, the voltage of the capacitor is behind the current in the circuit by 90 degrees. So the voltage of the capacitor is like this. Okay? And the voltage of the inductor, a minute ago we saw that the voltage of the inductor is ahead of the voltage of the source. Or the voltage of the inductor is ahead of the current. Now, a minute ago, we only had the inductor or the capacitor. Therefore, the voltage of the source was equivalent to the inductor. I should put like this. Sorry. Let me do it this way. This is the voltage across the resistor is equal to IR. Okay? So therefore, the current in the circuit is in phase with the voltage of the source. So this is, let's say, omega t. Okay? And this is omega t plus pi over 2. So basically what a phasor is a vector that's rotating, whose angle is changing as a function of time, omega t. And the voltage of the inductor is ahead of the voltage of the resistor by 90 degrees. How do I know that? Well, because the voltage of the resistor